Okay, so galvanic cell is associated with positive voltage. Well, if it's a negative voltage, you have something called an electrolytic cell. And because that's
Dr. Wendell,
yes.
I have a question. So on 710, I see that they use 0.77 minus 0.34.
Mhm.
But if we're doing cathode minus anode, and I know we're changing 0.77 from negative to positive because
Mhm.
it's gaining. Wait, actually, yeah, it's gaining. So it should be negative 0.77 minus 0.34. Why is 0.77 positive?
I like your question. Let's take a look at that for just a second here. Okay, so I'm looking back in our table just to be sure they didn't create a little typo for us there. And I'm looking at, yeah, I think they actually made a mistake there. If you look carefully on page 709, the standard reduction potential for iron 3 becoming iron 2. Do you see the number that is associated with that? Iron 3 becoming iron 2.
Um,
Do you see where iron 3 is becoming iron 2? We're looking at the
oh,
left side
oh
of the
yeah, it's
table.
positive.
That is a positive. I believe that that's a typo where it says E cathode equals negative 0.77. I don't think they meant to say that.
Oh, okay.
Okay. Because if you look then at 2 lines below where they've put that negative 0.77, they've written it again as positive
Oh,
0.77.
okay.
So I do believe that's an error where they wrote the potential for the cathode.
Okay.
All right.
Are we subtracting the absolute value then?
They're doing something very weird there. Okay, so let's take a look at the oxidation of copper to copper 2. And in this table, I see that it is negative 0.34. So what they're really doing is taking the number 0.77 and subtracting 0.34. And so again, Rena, I think that their use of the negative sign here is simply confusing. And I would urge you to go back to the way we did it, where we're simply adding the inverse of the reaction. I think 708 is a much clearer definition of what's going on than what they're trying to show you at the bottom of 710, especially with that typo that's there.
So negative 3.34 is the reduction potential, but we now want the oxidation potential.
Um, 0.34 is the reduction potential. We want the oxidation potential. That's where negative 0.34 comes from.
Oh, so negative is the oxidation potential.
That is right for copper. Mm-hmm.
But on 708, it doesn't specify that it's
Well,
oxidation.
let's take a look at that then. Let's go back to page 708. Okay.
Oh, it's just the reverse. Okay, I got it.
Okay. You sure?
Yeah.
Okay, cool. This line notation is useful. It gets a little complicated, but I'm talking about the bottom of page 711. Let's just talk about that line notation for a moment. We focus first on the double lines. The double lines. The double lines indicate the separation of the two beakers that we talk about when we do electrochemistry. And so on the left side of the double lines, we have the anode reaction. And so magnesium is the reactant and magnesium ion is the product. But since magnesium ion has fewer electrons than magnesium atoms, this is the side from which electrons are generated. And now we look to the right of the double lines. And on that side, we find aluminum ions becoming aluminum atoms. And that requires electrons. That's a reduction. So the right-hand side is always the cathode reaction. So when I look at line notation, I'm looking at the double lines, and on the left, I'm seeing the anode, and on the right, I'm seeing the cathode. And then I have to figure out how electrons play into both of those reactions. So what I'd like you to try, let's write out that anode reaction. Let's write out the cathode reaction. Let's combine those and write the net reaction, which lacks any free electrons. And then hold that up to your camera. We'll take a look at what you got.
Dr. Winslow, I have a question. If you look at a diagram without the reduction potential and without the balance equation, can you still determine which one's the cathode and which one's the anode? No, right?
Only if the diagram indicates the flow of electrons.
Oh, so if it's flowing into, then that's the cathode.
You are correct.
Okay.
Mm-hmm. So here we're trying to go from a line notation to a net reaction.
Is that for Fe and copper?
No, we're down at the bottom of page 711. So we've got magnesium and aluminum involved. So take a look what I've put in the chat box. Unfortunately, I can't make superscripts, but is that the balanced equation you got?
What does the 3 aqueous mean?
That means that aluminum has a +3 charge. That should be a superscript.
Yeah.
And that magnesium has a +2 charge. And again, I can't do the superscripts in Zoom. Now, I want you to go back to our standard reduction potential table and figure out what the voltage of this reaction is.
Is it 0.71?
Very good.
I got the same number.
Yay.
I
So-
typed it in the chat.
Very good. So I'm glad that we didn't multiply either equation by anything, even though we had to multiply magnesium by 3 and aluminum by 2. We don't mess with the voltage that way. So hold on just a second here. Okay. All right. So now we're on to something kind of tricky. I'm going to kind of gloss over this, but at the same time, we want to take a look at some things that are going on here. So we're on to page 712. Ay, caramba. Above the blue lettering that says complete description of a galvanic cell, we have line notation that just precedes that. And so I'd like to go through what the heck is going on here. So it begins with PT. Any ideas what PT is? Do we see that we're beginning with PT solid? Any ideas what PT is?
Is that on 712?
We're on 712. We're just above the blue lettering that says complete description of a galvanic cell. And just above that lettering is a whole list of things written in line notation.
Particles?
Okay. What does PT stand for? I'd like you to flip back to page 707. 707. And there we see PT again. What the heck is this PT? Hint, it's on the periodic table.
Is it platinum?
There you go. Platinum is an unreactive metal. It's also very expensive, hard to find because it is so unreactive. So we know that on the left side of double lines, this is the anode. Somehow we're getting electrons out of the chlorate ion, which is ClO3 minus, and the perchlorate ion, which is ClO4 minus. Somehow we're getting electrons out of that. And in the process, those electrons are being transferred over to something called permanganate and manganese 2 ion. And all the while, there's another piece of platinum sticking into a beaker somewhere. So if you look now at the bottom left of page 712, figure 18.7, the cathode is the same as what I just described. The cathode is a platinum wire sticking into a solution, and that solution contains 3 solutes. We have 1 molar hydrogen ion, 1 molar manganese 2 ion, and 1 molar permanganate ion. Now let's look underneath the text of figure 18.7, the schematic of a galvanic cell based on these half reactions. Let's look at MnO4 minus. What's the oxidation number for Mn in MnO4 negative? What's the oxidation number for Mn in MnO4 negative? Just as a quick reminder, oxide is going to be -2, and there are 4 of those. So what is the oxidation number for manganese in permanganate ion?
Is it 7?
You are correct. When we add 5 electrons to something that has an oxidation number of 7, the oxidation number becomes +2. We're adding 5 electrons to the manganese atom in permanganate. As a result, Mn is going from a +7 to a +2. But now those oxygens aren't nearly as attracted to Mn. So those oxygens, they become water. Why? Well, because this is constantly taking place in an aqueous solution. We assume that all ions will be in an aqueous solution. Now let's go back up to closer to the top of page 712. We have just written down the cathode reaction. We got to figure out this anode reaction. Okay, now there are going to be some similarities between the cathode and the anode reactions for this particular case. But let's try to figure out what the heck is going on in our anode. So would you please write the chlorate ion? That is ClO3 minus. ClO3 minus. From ClO3 minus, we have an arrow that points to ClO4 minus. I have ClO3 minus on one side of my arrow. I have ClO4 minus on the other side of that arrow. We are trying to construct an anode reaction. Now, here's the weird part. Where the heck did oxygen come from? How can you go from ClO3 to ClO4? Well, water. So would you please add H2O on the reactant side? Now I have H2O plus ClO3 minus with an arrow going to ClO4 minus. That's not balanced. How are we going to balance this equation? What is the other thing that's present in our beaker besides ClO3 minus? Water, because that's what AQ means, and ClO4 minus. There's one other thing that's present in our beaker besides water, ClO3 minus, and ClO4 minus. What else is present?
Is it hydrogen ion?
Hydrogen ions. Notice this is not hydrogen gas. This is hydrogen ions. How many hydrogen ions would we put on the product side to balance our equation?
2.
2. Now there's a small problem. If I look carefully on my reactant side, I have a net of -1 charge. But on the product side, I have a net of +1 charge. That's not balanced. But if I add 2 electrons to the product side, I now have a net of -1 on both sides, and I have an oxidation, meaning I've completed my anode reaction. ClO3 minus is undergoing oxidation to form perchlorate and hydrogen ions and 2 electrons. Now, we said before that oxidation is the addition of oxygen. Well, guess what? We just added oxygen to chlorate to make it perchlorate. Oh, we also said that electrons have to be on the product side for oxidation. And guess what? The electrons are now on the product side. So those definitions that we talked about, they're very useful. They kind of reinforce each other. Let me close my door. I'll be right back. So what we're doing is something called balancing equations by a half-cell method. We're also learning something about line notation. And the one thing that people forget, AQ means that H2O are available. You can use them. And this is the first time when we've seen the symbol AQ and we've actually changed water. But that's what happens in electrochemistry. Now, we have 5 electrons that are involved in the reduction of permanganate ion. But we only have 2 electrons coming from our oxidation. Uh-oh. What are we going to do to create the overall reaction? Hint, what is a common multiple of 2 and 5?
10.
10. So where you see 5 electrons, everything in that equation has to be multiplied by 2 to keep it balanced and to have 10 electrons. In an equation where you see 2 electrons, everything has to be multiplied by 5 to keep it balanced. But once you have 10 electrons as products and 10 electrons as reactants, you can add those 2 reactions together.
I'm so sorry I have to go because I have a prefect interview, but I'll watch the video when you upload it.
Sounds great. I'll make sure I do that right away.
See you. Bye.
Bye-bye. So Rena, can you hold up the net reaction when we add our oxidation with our reduction and cancel out 10 electrons from each? When you've got that balanced, hold it up to your camera. Take a look at what you got.
I don't know if this is right. I don't think this is right. I just like wrote down a bunch of
Pull it back ever so slightly. Come closer again for me. Sorry. It's the lighting that's a little weird. You did that almost exactly correct, but somehow I don't see 5. Oh, now I think I see 5 in front of ClO3 minus and 5 in front of ClO4 minus. Do I see a 5 in front of ClO3 minus and a 5 in front of ClO4 minus?
Oh no, I didn't like multiply through.
Yes, you have to multiply through.
So then would the hydrogen, would it have like 16 in front of it and everything?
Yes, you're going to be doing all of that. Not 16, it should be 10 in front of hydrogen for the ClO3, ClO4 thing.
But what about for the manganese with?
Then yes, it will have 16 H's in it.
And then we combine both. I combine both of those reactions.
That is correct.
Okay.
And then we may do some canceling out of hydrogen from one side to the other.
Okay. So then does the hydrogen cancel out completely from the perchlorate reaction? And then there's just 6 left in the manganese one?
That is correct. Mm-hmm. So Rena, when you've got this finished, my question to you is, how many water molecules and where are they?
Is it 3 water molecules on the product side?
Exactly. Very good. So this is called a method of balancing via half-cell reactions. The simplest is to use water as the source of oxygen and hydrogen ions as the source of hydrogen atoms. And they are available because you're in an aqueous solution. Water surrounds these things. So let's look now both at the bottom of page 712 and up at the top of page 713. We have at the top of page 713, or near the top, I shouldn't say at the very highest point, we have a line representation that matches the schematic diagram of figure 18.7. Now, the textbook is doing that pretty frequently. They're also doing it down at the bottom of page 713. So Rena, the idea of starting from a diagram such as you see in figure 18.7, going from that diagram and trying to draw the line representation of that is a very good idea. And then if you look at the bottom of page 713, if you cover up the diagram, look at the line representation, can you go from the line representation to a sketch of the 2 beakers, the 2 pieces of metal, the flow of electrons in the salt bridge. So that's something that I would practice just a little bit. I wouldn't spend, more than say 10, 20 minutes on that, but I think that's worth practicing. Now, you said that you had some questions. So before we start diving into some real conceptual stuff that's going on here, do you have any questions from those first few sections that we just looked at, 18.1 and 18.2?
No, I don't have any questions from those.
Very good. So I have a feeling that your questions are going to begin on page 715. Is that true?
Well, I just had questions from, I took some multiple choice questions. And
oh, very good. Let's do that.
Okay, I need to go get the book then.
That sounds great. So why don't you hold it up to the camera and we'll see what we can see. And if I can't see it well, then I'll have you take a picture and send it to me.
There's the standard reduction potentials on the bottom, but the rest of the questions are on the other column.
Okay, so we're looking at a very simple standard reduction potential table. Yeah, that's just not going to be clear enough for me to be able to see. So if you read those out loud, we should be able to get through them pretty well.
Okay. The first one says a student conducts an electrolysis cell with 2 inert electrodes in an aqueous solution that is 1 molar cesium nitrite and 1 molar cesium hydroxide. As the cell operates, an odorless gas evolves from one electrode and a gas with the distinctive odor evolves from the other electrode. Choose the correct statement from the following list. The odorless gas is oxygen. The odorless gas is the result of reduction. The gas with the distinctive odor is the result of oxidation, and the odorless gas evolves at the negative electrode.
Okay, so let's break down the question a little bit, but before we start looking at those responses. Electrolysis means that someone is applying external energy to make an unfavorable chemical reaction take place. This is the equivalent to photosynthesis, where the plants are taking in sunlight to make a chemical reaction that shouldn't happen actually take place. So electrolysis is the opposite of a galvanic cell. Okay, so now nitrite. Would you please look carefully in the in the reduction potential table that you are given? Does NO2 minus appear anywhere in that reduction potential table?
No.
Okay.
Oh, wait, yeah, it does. It does. One place.
Okay. So we need to know that nitrite is NO2 minus.
Mm-hmm.
Okay. Would you please very slowly read aloud the reaction that involves NO2 minus, nitrite?
NO2 minus aqueous plus 5 H2O liquid plus 6 E minus goes to NH3 aqueous plus 7 OH minus aqueous.
I'm sorry, the very last thing that you said?
7 OH minus aqueous.
Very good. Okay. Now, let me read it back to you just to be sure that I didn't miss something. I have NO2 with a negative charge, aqueous, plus 5 H2O liquid, plus 6 electrons, becoming NH3 aqueous plus 7 OH minus.
Mm-hmm.
Okay. Now, the first thing I want to underline is NH3, because NH3 has a very distinctive odor.
Mm-hmm.
Okay. Now, would you go back and after it mentioned cesium nitrite, by the way, where is cesium found in the periodic table?
Is that an alkali metal?
And therefore?
It will dissolve in water.
And? serve as a spectator ion.
Yeah.
That's why it's not present in the equation that we've just written. Now, what is the other substance that was mentioned besides cesium nitrite?
Cesium hydroxide.
Okay. Now, in your potential table, do we have a potential for hydroxide ions becoming oxygen?
There's
We're looking for.
oxygen becoming.
Sorry, go ahead.
There's oxygen becoming a hydroxide ions.
Ah, very good. So you have a balanced equation that looks like the following. O2 plus 2H plus 2 electrons, 4 electrons, becoming 2 OH minus.
They used 2H2O and then becomes 4 OH minus.
2H2O plus 4 electrons.
And O2.
4 OH minuses. Okay. So that I end up with 4 O's. Okay. Let me read it back just to make sure we're talking about the same thing. I have O2 plus 2H2O plus 4 electrons becoming 4 OH minus.
Yeah.
Okay, good. Okay. So this means that we have the reduction of nitrite to ammonia. And then we're going to flip around to convert 4 hydroxide ions into oxygen and water. Before we get any further, would you please tell me what is the voltage that they associate with the formation of ammonia from nitrite ion?
Negative 0.15.
Negative 0.15. Okay. What do they assign? What voltage is assigned to O2 plus H2O plus 4 electrons to make 4 hydroxide ions?
Positive 0.4.
Positive 0.4. Okay. Now, electrolysis means we want a net negative voltage. Electrolysis means we need a net negative voltage. So which of these two reactions is going to become our oxidation?
The formation of hydroxide.
That's right. We're going to turn it around, and those hydroxide ions are going to decompose into 2 water molecules, oxygen gas, and 4 electrons. And that's going to have a negative 0.4 voltage. So we have now an oxidation normally taking place at the anode. And this is an electrolytic cell, so we can make that statement and not have to modify it at all. So we're generating 4 electrons as hydroxide ion decomposes with a negative 0.4 volts. We have nitrite ion being converted to ammonia with a negative 0.15 volts. Now, let's read those choices again.
The odorless gas is oxygen. The odorless gas is the result of reduction. The gas with the distinctive odor is the result of oxidation. The odorless gas evolves at the negative electrode?
Okay. So the odorless gas is truly oxygen. The other gas, the one that can be smelled, and I forget exactly how it was put, that's NH3.
Mm-hmm.
Okay. Oxygen is being produced at the anode as a result of oxidation. Ammonia is being produced at the cathode during reduction. So which of those four choices is consistent with what we've just learned?
A, the odorless gas is oxygen.
I believe that's the only question, the only response that makes sense. Okay. But please do read for me B again, just so I can hear it.
The odorless gas is the result of reduction.
That can't be true. Go ahead.
The gas with the distinctive odor is the result of oxidation.
Again.
The odorless gas evolves at the negative electrode.
Not in this electrolysis. So yes, A is correct. So what we had to do there was to look very carefully at their standard reduction potential table, realizing that they're talking about compounds and polyatomic ions. The majority of substances in the standard reduction potential table we looked at involved elements. Okay. So focusing on what's being presented in the question is going to be key.
Mm-hmm.
Okay. So what other questions do we have? Multiple choice questions are great.
Okay, the next one was another student attempted to prepare the electrolysis cell to produce aluminum metal from an aqueous solution of aluminum chloride using a 6-volt battery. The cathode compartment of the electrolysis contained 1 molar aluminum chloride, and the anode compartment contained 1 molar calcium chloride. The student was unsuccessful. Why was the student unable to produce aluminum metal?
Let's talk about that for just a second here.
Mm-hmm.
Describe the two beakers one more time for me.
The cathode compartment contained 1 molar aluminum chloride, and the anode compartment contained 1 molar calcium chloride.
Aha. Is there any mention made of what is put into each of these electrodes? What metals we're talking about, I mean?
The beginning says electrolysis cell to produce aluminum metal from an aqueous solution of aluminum chloride using a 6-volt battery.
And calcium chloride in the 6-volt battery. Okay. Okay. We're going to take a look at our standard reduction potential table. Is there one given for this problem?
Yeah, it's this like a group of problems with this one.
Good. Does it give the reduction of calcium?
I don't see calcium.
Okay. Then let's look very carefully in our reduction potential table to make sure that aluminum chloride is not one of our reactants. I certainly see aluminum ions, but I am checking that aluminum chloride, not given. Okay. So what voltage is required to reduce aluminum ions to aluminum atoms?
Negative 1.66.
So we must apply a voltage that exceeds positive 1.66 to make that happen. Aha. We are supplying electrons, and so those electrons are coming from whatever is being oxidized on the other side, on the other beaker. Since we don't know what metal is being used at the anode, we're going to have trouble answering this question. However, it's a multiple choice question. So let's take a look at those choices now.
Mm-hmm. The first one is the voltage from the battery was insufficient to force the reaction to occur. Reduction of chloride ions occurred in preference to reduction of aluminum ions. Aluminum chloride solutions do not conduct electricity, and reduction of water occurred in preference to reduction of aluminum ions.
Very good. That's great. Okay. So let's go through these choices without doing a whole bunch of crazy calculations.
Mm-hmm.
Okay. So they mentioned the oxidation of chloride ions to chlorine. Let's take a look at that. I'm looking on page 709. Is that given in the problem? 2 chloride ions going to chlorine plus 2 electrons?
No.
Okay. So that's a bit of a red herring. We won't talk about that. I'm just going to look at it right now. Yeah, so that voltage is, okay, that's fine. Okay, so the voltage of the battery being too low, that's not really possible. Why? We talked about the lithium fluoride battery and it having a voltage of something around 5, but not 6 volts. So everything in between those two could be run in reverse by a 6-volt battery. It's impossible to create a greater voltage than that, so we know that's true. So our choice A is out. A 6-volt battery is more than enough to reverse any of the combination of reactions that we would have in that very large table. And now it says B, the reduction of chloride. Could you help me with the wording there? The wording is key here.
Reduction of chloride ions occurred in preference to reduction of aluminum ions.
Okay. Is it possible to reduce a chloride ion?
No.
Because?
It's already been reduced.
It's already been reduced. Its valence shell is full. It's going to behave now like a noble gas. There is no more room. Okay, got it. Okay, so because chloride ion has all the electrons it can have, that reduction is not possible. What was the next point?
Aluminum chloride solutions do not conduct electricity.
What are they trying to tell us about aluminum chloride in their description just then?
That it's aqueous.
Right. They're trying to tell us that somehow aluminum chloride is a precipitate that can't react. But we know that chloride ions tend to be very soluble, and aluminum being high in the periodic table means it's more likely to be soluble than if it were low down in the periodic table in the presence of chloride ions. So I think we can eliminate that choice on the basis of we know that aluminum chloride is in fact very soluble.
Yeah.
So what's our last choice?
Reduction of water occurred in preference to reduction of aluminum ions.
And that makes the greatest sense. Let's take a look at what we're talking about there. I'm looking for reducing water. There it is. Take a look on page 709. Notice that the reduction of water to hydrogen and hydroxide ions, that reduction is unfavorable and it's a negative 0.83. However, it's less negative than the reduction of aluminum ions to aluminum. So we can confirm that fourth choice, item D, by a careful examination of the standard reduction potential table. Was that voltage of negative 0.3, does that appear anywhere on the standard reduction potential table that was given?
Negative 0.3?
Negative 0.83.
Yeah, that's there.
That's part of that table. So they did want us to make that comparison and to look carefully at how those reductions are taking place.
Mm-hmm.
So this is what we're learning, that our standard reduction potential table is a summary of how all of these substances can interact with each other. We are looking for the most positive voltage or the least negative voltage for a reaction to occur. Electrolysis implies a negative voltage. Batteries, galvanic cells, voltaic cells, those are synonyms for something that has a positive voltage. So let's take a look at more multiple choice questions.
Okay. There's two more.
Good.
It says, which of the substances in the table would be capable of reducing the aluminum ions in solid aluminum chloride to aluminum metal? Assume the cell potentials in the table also apply to the solid state.
Okay. Before we start looking at those choices, let's look at page 709. Give me an example of a metal that could potentially serve as a reducing agent to cause aluminum to undergo reduction.
So would I be looking for something that's greater than 1.66?
The answer to your question is yes. Remember, we're going to be oxidizing that metal, and the voltage of that oxidation should be greater than positive 1.66. Yes.
But then I would like take the absolute value of one of the ones, because I want.
It's not that you're taking the absolute value. It is that you're reversing the reaction and therefore changing the sign.
Okay, so then it would, like, magnesium could work.
Very good. Magnesium, lanthanum, sodium, calcium, barium, potassium, or lithium would all suit the question that you just read, because it mentions things being in the solid state without any water present.
Mm-hmm.
And the problem with sodium, calcium, barium, potassium, and lithium is if you put them in water as metals, they react directly with the water.
Yeah.
Okay, so now we go back to the choices that were given to you in your prompt, the standard reduction potential table that you're looking at. Does it have any metals below aluminum?
It has cesium.
And we don't have cesium on our list. So what is the voltage for the reduction of cesium?
2.91.
Okay, and that should be negative for the reduction. And so 2.91 for its oxidation.
Mm-hmm.
Is there any other metal below aluminum on the list that they have given you?
They have, let me check if it's below.
We want to just focus on that particular question because these standard reduction potential tables can get really long.
Mm-hmm.
And we're just trying to figure out what we're limited to in terms of the choices they're offering.
No, they didn't give anything below.
Very good. So now let's look at our four choices.
Chromium, cesium, silver, or none.
Very, very good. So we know now that cesium is the correct metal.
Mm-hmm.
And that's just getting comfortable with the standard reduction potential table that we're presented with.
Mm-hmm.
So if you are doing the exam and you turn a page and suddenly, hey, there's a standard reduction potential table, before you start reading any of the questions, figure out what you've got there, where things are, How long is that list? How short is that list? That kind of thing.
Mm-hmm.
So next question.
I got this one right. I don't remember if it was a guess or I actually got it right, but a student constructs a galvanic cell that has a chromium electrode in a compartment containing 1 molar chromium-3 nitrate solution and a silver electrode in a compartment containing 1 molar silver nitrate solution. A salt bridge containing 1 molar potassium chloride solution connects the two compartments. The student used the following 2 half reactions from the table. And it was reduction of silver and chromium.
Well, it's the reduction of silver and the oxidation of chromium.
Wait, reduction is when it loses an electron?
No, that's
gains an
oxidation.
electron. Okay. So then they're both reductions.
Right, but we have to turn one of them around.
Yeah.
Okay. And I believe the answer is going to be 1.53 volts. Was that one of the choices?
Well, the question was asking when the student measures the cell potential, the value is far from the ideal predicted value. What is the cause of this discrepancy?
Okay, read to me the whole question in its entirety then.
From the beginning?
Yes, please.
A student constructs a galvanic cell that has a chromium electrode in a compartment containing 1 molar chromium-3 nitrate solution and a silver electrode in a compartment containing 1 molar silver nitrate solution. A salt bridge containing a 1 molar potassium chloride solution connects the two compartments. The student used the following 2 half reactions from the table, which is silver and chromium-3. And then when the student measures the cell potential, the value is far from the ideal predicted value. What is the cause of this discrepancy?
Is it the precipitation of silver chloride?
I said the potassium chloride in the salt bridge interfered with the reaction.
Absolutely. What are the other choices?
The initial concentrations should have been lower than 1 molar. The initial concentration should have been higher than 1 molar. And the student did not allow the cell to come to equilibrium.
Your intuition was perfect on that one. 1 molar is the standard state to obtain the voltages we see in a standard reduction potential table. But the suspicious thing was the mention of potassium chloride as opposed to potassium nitrate, which would have made much more sense. So you're absolutely right. The chloride ion is going to precipitate the silver ion. When the silver ion concentration goes low, the voltage in this battery is reduced because you don't have the silver ions to attach to the silver metal, which is a key step in this particular cell. Okay, that was an hour and a half on electrochemistry, and it sounds like we're making some real progress too. Good. All right, I will see you tomorrow then.
Okay.
All right. Glad you joined me today.
Okay.
See you tomorrow.
Bye.